I'm going to talk to you about the science of measuring carbon, but before I do that, I just like to thank Pew Trusts for putting on this conference and for inviting me to speak. I really appreciate the opportunity. Okay, so the questions I'm going to try to answer for you is how much carbon is sequestered in the WA Outback, where is it held, where is it stored, and how much more could be stored. So these are fairly important questions, but I have to say that we don't have all the answers as well as we would like to be able to answer those questions. So I'll do the best I can. I'll attempt to answer those questions in this presentation structure. So I'll be starting off with some background information on studies that have been done throughout the rangelands or the outback. The body of the talk revolves around what I call land system characterisation. So I'll delve into that in more detail. And then there's a short section on how I see the future in terms of measuring carbon, and then I'll just wrap up with some key statements, key messages for you. Okay, some background. So this map of Western Australia, fuzzy, shows where the major projects have occurred throughout the rangelands that include a fairly major component of carbon in their studies. Some of the studies were multidisciplinary, with carbon as one of the components. Other studies were dedicated to carbon. A range of organisations have participated in the carbon studies. Department of Agriculture has been big in the field. Department of Parks and Wildlife, it has also done some work in biomass carbon. The University of Western Australia, through their ecosystems group, have done quite a lot of biomass carbon work as well. And Rangelands NRM has also done quite a bit of work. And most of that, in fact all of that, was with public funding. There are also some studies that have been done on a smaller scale, usually using private funding. So the result from all this work, some of these studies are very site-specific and others are much more extensive. But the net result of all that is that we have information of variable use for about 26 land systems. And I'll briefly explain land systems as we go along. So there's a lot of information out there, and there's reasonable coverage across the regions of Western Australia, but it's still relatively sparse information in terms of the size of the state. So there's still a long way to go. Okay, there have been studies, Australia-wide studies, including this one as an example from CSIRO. This is the amount of carbon sequestered in our soils across Australia. And you can see that across Western Australia, it's just over 7 gigatons of carbon is the estimate.
So for people who can't see at the back, that's higher than anywhere else, is it?
It is. It is higher, mainly because of the size of the area, the large size.
So it's
Okay.
not per unit area, that's for
No,
the
that's the
whole
total
area.
stock.
Right.
Yes,
Okay.
that's right. Just thinking about the rangelands themselves, there's probably about 2 gigatons in the intensive agricultural area of the southwest of WA. So that would leave about 5 gigatons in the soils in the outback, the rangelands. And we can probably double that if we include the above ground biomass vegetation. So probably somewhere around 10 gigatons. My database is gigabytes. Gigatons of carbon stored in our outback. But the error bars on this estimation are fairly long. Certainly for Western Australia, the Yarrabahs are the biggest. There's not been a lot of calibration on this work. Over east, they had much more calibration. So the Yarrabahs are smaller. Okay, let's move on. So just want to talk about the Carbon Awareness Project, managed by Rangelands NRM, which ran from 2013 through to June this year. Royalties region funded, and it had two main objectives. The first objective being raising the awareness of carbon abatement amongst people managing land in the rangelands. So the idea was to try to explain what carbon abatement is about, the two types of abatement, emissions reduction and sequestration, trying to tailor the information coming out of the Australian Government through the CFI, Carbon Farming Initiative, and then the ERF, the Emissions Reduction Fund, and tailoring that information so that it had more meaning and relevance to the land managers in the Western Australian Outback. So we had field days involved on our demonstration areas, and basically passing on this information to help them appreciate what carbon farming might be about. Quite difficult at times because we didn't have any real case studies to actually use as examples, but we had good turnouts at most of our field days, and a lot of interest, a lot of follow-up interest, lots of phone calls saying, could you answer this for me, please? Okay, so that was a success there. The second objective was the provision of sound science. And the approach we took in doing the science was that it needed to be practical. It needed to be applicable to carbon farming or someone wanting to undertake a carbon farming project. So it wasn't dealing with the more esoteric stuff such as carbon flux, the forms of carbon that it takes in the carbon cycle. It was about how much carbon is there or could be there under different management. So we did studies on several properties, and on each of these properties we did the studies in areas where there was a proposed change of land management. It could be, or was, a change of grazing strategy. There was a conversion from grazing property to a conservation reserve, so we studied in there. There was another property had a large-scale rehabilitation plan, so we got in there before they'd actually done the rehab and did the benchmark study there. And in all these studies we've done what we call the benchmark, not baseline, but benchmark studies, and then in due course, in years to come, someone, probably not me, will go back, resurvey and see what the effect of that change management has been on the carbon stocks. So this section is about land system characterisation. So it's understanding the nature of carbon, where is it distributed in the environment. So you'll probably recognise this from your school days. This is the carbon cycle. The plants are the drivers of carbon, the carbon cycle. Without plants, the carbon cycle will fail, or does fail. So carbon is sequestered in plant tissues and in the substrate the plants are growing on, whether it's in water, in the mud in the water, or on land in the soil. And that's driven by the plant processes themselves. So respiration of the plants, transpiration by the plants, photosynthesis, with the energy of the sun, of course. So that's where the carbon is stored, the organic carbon. Okay, so what land system characterisation is about is trying to understand where that carbon is distributed. And we use a land system as a basis for that, and I'll describe that shortly. So the information or the data that we gather about land systems in terms of the carbon is what we call the carbon density, which is the concentration of carbon per unit area, so tonnes of carbon per hectare, for example. The carbon stocks can be calculated once you've got that figure for a defined area. So let's say you've got 7 tonnes carbon per hectare and you've got 10 hectares. There's 70 tonnes. That's the stock, the carbon stock for that defined area. Okay. Also, the carbon is distributed or partitioned between the above ground plant matter and the below ground in the soil. Okay, so that's a characteristic of particular land systems. And of course, when you're doing this measuring, you also must know how variable those measurements are across the landscape or across the land system. All of that is dependent on the climate, the intrinsic characteristics of the plants, or the vegetation assemblage, and the soil types, and of course, the land management. What is happening on that land in terms of what land use is being done there and how well that land use is being done in terms of the ecology. So here's a description of what a land system is. It's an area of land with a recognisable association or combination of particular land types, vegetation assemblage and topography. So as soon as you hear the term land system, just think soil, veg and topography and you'll get the guts of it. So land systems are actually a part of a hierarchical classification of the landscape. And PJ Waddell, a bit later on, will give you a lot more information about land system mapping. But the land systems form the basis of our carbon work. We couldn't do the carbon work very well without knowing the land systems and the subdivisions within land systems. So here's an example of land system characterisation for a particular property in the northern Pilbara. There's a sequence of 3 slides here showing different data which together characterise a land system. So this map has, we worked on 6 land systems on this property, and this property was about to undertake a change from continuous grazing to a seasonal-based, rotational, rest-based grazing strategy. So we got in there and did the benchmark carbon work, and was also supporting Landgate in their study of the biomass and change through time. So this map is showing the mean above ground carbon stocks, density or concentration for the 6 land systems. Just take note of the scale bar, it's 20 kilometres, so it's quite a big area, about 60,000 hectares. And we also did sampling outside of the trial area, the grazing trial area, so that we could get in time a change that might be due to the changed grazing strategy. Oops. So that's above ground carbon. What's important here is that the values of carbon in the above ground reflect the type of vegetation. So the lower values that you see on the map there, the black numbers, pertain to grass-dominated land systems. The higher numbers relate to those land systems where there's a much higher component of woody vegetation, in other words, the woody shrubs and trees. If we go to the next slide, this is the mean below ground carbon concentrations or density for the same 6 land systems. And you can see here differences in the numbers as well. So the higher numbers of carbon density pertain to those soil types on the alluvial plains that are clay rich. Clay and silt are able to bind organic carbon much more than a sandy soil, for example. So the lower values here pertain to those land systems that have a sandy, more sandy type soil.
Excuse me, those like 19, is that tonnes per hectare or CO2 equivalent?
It's tonnes C, yeah, not CO2 equivalent, it's tonnes C. And the last slide is the ratio or proportion of that carbon held above ground as a proportion of the total carbon stock. So you can see there, obviously for the same 6 land systems, that the higher numbers, the higher proportions, relate to those land systems that have a woody vegetation and a poorer soil. So a more sandy soil carrying this carbon up below the ground. And the higher numbers relate to those land systems that are grass dominated, growing on deep clay-rich alluvial soils. And this is an important characteristic of all the land systems. They will have some intrinsic characteristic, a ratio of above ground to the total stock. Okay, let you in on a bit of a secret here with soil carbon. It has been common practice when analysing soils for carbon, to divide the soil sample into 2 main fractions, a -2 millimetre fraction and a +2 millimetre fraction. No problem with that. In fact, it's very useful for other reasons. But what has happened is that the carbon content in the +2 mil fraction has often not been analysed. Certainly been analysed in the -2 mil fraction, and that's a lot of the figures that you'll see around are just relating to the -2 mil fraction. But as you can see from that table, there are some land systems, the one on the right there has a high proportion of carbon in that coarser fraction, 34%. It doesn't matter for the other land systems where the coarse fraction holds little carbon. For example, the low one there, the 1%, immaterial in the scheme of things. But where the carbon content in that coarse fraction is above, say, 20, perhaps even 15, then it needs to be counted into the carbon stock calculation. Okay, still on land system characterisation. This is 2 land systems, very different, so it's a contrast. One is located in the Pilbara on the grasslands, on deep alluvial soils. The other, the lower one, is located in the Murchison, in the Mulga country, on a very shallow, loamy, hard pan type soil. Using the mean values for these 2 land systems, these represent N members of a spectrum that ranges from very low to higher. And if we look at the percentage of carbon held above ground compared to the total carbon stock, that is the above and below ground added together as the divisor, we end up with some figures. Where's the pointer? So these figures here, 23 and 84. And these figures are reasonably common, but most land systems will lie between those 2 endpoints, N members on the range or the spectrum. So I call it the rule of thumb is the 80-20 rule. So land systems may range from 80% above ground to 20% above ground. Of course, there are outliers. Some land systems will be more extreme, but in the main, many of the land systems, in fact all the land systems we've studied so far, lie between these end members. Okay, so this is about some of the problems of actually measuring how much carbon is in the above ground plants, the biomass. So and the difficulty is because the plants have different growth forms, in other words, grasses, shrubs, trees. They are different sizes, different shapes, and the tissue in each of those plants contains a different amount of carbon or has a different carbon concentration. Soft materials such as leaves and the fronds or leaves of grasses, roughly 37% carbon, whereas the woody material in the trees and the woody shrubs, 47% roughly carbon constitutes that tissue. So the work that we've done has actually solved this problem in a way that's very neat and provides very useful solutions and information for the future. I'll explain that soon. So the important findings relating to the land system studies is that we have been able to quantify the relative distribution of carbon amongst the plant forms. So we can recognise a plant form and work out fairly quickly how much carbon it is likely to contain. We've been very fortunate in being able to develop a pretty simple group of equations, basically species or life growth form based equations that describe or calculate the amount of carbon for each of those life forms. And that equation in green on the screen there, you'll recognise from your early school days. It's just a basic linear equation, with M being a parameter related to the growth form of the plant.
2 minutes, Peter.
Okay, nearly done anyway. Okay, so, and as it turns out that the relevant or useful metrics from the plants are also useful, are easily measured in the field and are probably applicable to remote sensing. And we'll be hearing from Simon and Russell after me, talking about the remote sensing applications and possibilities. And I'm very, very excited by that. I'm not going to divulge those actual parameters because we're in the process of publishing, so we want to get it out there before it actually becomes public. So what next in carbon farming? So this diagram illustrates how the field data from the Rangelands NRM work, or carbon awareness project that we ran, and the previous work that Mark Olchin did on the carbon capture project, all that information and others is very useful field data. It's all field data collected, and that will feed into computer modelling, decision tools, and remote sensing. And then obviously those tools will be used to help carbon farming, particularly in the feasibility stage, to decide whether to go ahead with the project or not. Okay, so the key messages are that there are huge amounts of carbon in the Western Australian Outback. There is an opportunity to substantially increase those carbon stocks. You would have noticed a few slides ago the range of values for the above ground and below ground carbon for 2 of the land systems. Those upper values represent the potential that you could increase the carbon that's sequestered there. So you can increase the carbon up to that level, or probably even higher. So there's a doubling or a tripling in many cases of that potential. I'm still optimistic about the future of carbon farming in WA, despite it being a roller coaster ride to date, but I still have a positive outlook on it. I have a plea though, and this is to take up Lynn's message when she introduced herself. Whatever you do on the land, do it with ecological responsibility. It also probably means, if you do it that way, that your bottom financial line will improve as well. Okay, thank you.